Welcome back, everyone. All right, so we're going to talk about Module 12 this week. Hypothesis testing. Yay! All right, so some of us have discussed this already, some have not, but when we're talking about a population parameter, of course, we're talking about either P, which is the population proportion, mu, population mean. And there's two different ways to test a proportion about a mean, which is one of which is the z-test, the other is the t-test. Four out of five dentists prefer Starbright toothpaste to other brands. 4 out of 5 is 80%. Okay, so that means that the population proportion of dentists is 80% that prefer that toothpaste. Fewer than 1% of dogs attack people unprovoked. P is less than 1%. In any given 1 year period, 9.5% of the population, or about 18.8 million people, suffer from a depressive illness. So this is not a percentage, but this is a percentage, you see. So this is not a mean, this is a number of people. So what we're saying is 9.5 out of every 100 people suffer from a depressive illness. That is still a population proportion, 0.095. For cars, the corporate average fuel economy has been 27.5 miles per gallon. Truck fuel economy has gradually increased to 22.2. So these are means, 27.5. And for trucks, 22.2. These are claims, all right? So just when we do science, like if you've ever done a science project or a science fair project, or you've ever judged one, you know that you have a hypothesis, you do an experiment, you test the hypothesis, and then you form a conclusion about everything. So that's sort of the process that we go through here. We're going to look at two hypotheses for each of these hypothesis tests, one of which is called the null hypothesis, or HO. That's the status quo. The other one is called the alternative hypothesis, HA. That's the research hypothesis, okay? These need to be opposites of one another. We're going to use an analogy later on with a courtroom and trying a defendant to understand these a little bit better, okay? So the null hypothesis contains the equal sign, so it's either equals, less than or equal to, greater than or equal to. The alternative hypothesis does not contain the equal sign, so it's going to have a greater than symbol, a greater than symbol, a less than symbol. Oops, shouldn't have done that. I was just underlining it. But anyway, a less than symbol here, a greater than symbol, or a not equal to sign. So, example, the machinery at a chocolate factory has been overhauled. The manager suspects that the chocolate bars produced are no longer falling within the 4-ounce average weight. Of course, the word average should indicate that we're talking about a mean, a population mean, so mu in this case. So the null hypothesis here is that the average is equal to 4 ounces. Well, then that means the alternative hypothesis indicates that the mean is not equal to 4 ounces. Sorry, I'm having a little technical difficulty. There we go. Okay. All right, so this is the status quo here. So the opposite would say that the mean is not 4 ounces. That's the alternative hypothesis. Specifically, and we can think about, if we've got 4 ounces here on the number line, if the chocolate bars weigh less than 4 ounces, who does that benefit? It benefits the company, right? It benefits the company because then they don't have to supply as much chocolate per bar, and the customer pays more per ounce. However, if the average is falling above 4, it benefits the customer, but the company loses profit. So, in the study, the null hypothesis is assumed to be correct unless the data disagrees significantly with it. And the process that we use to test the hypothesis is a very dispassionate process. It is the process of statistics. That's the work that we do to generate those statistics. If the data disagrees with the null sufficiently, we'll reject the null and assume that the alternative hypothesis is correct. So when we reject the null hypothesis, we have succeeded in our quest. We have succeeded in our, in the thing that we wanted to do. So the hope is that we can reject the null hypothesis. So one of the things we can do to practice is to identify the null and identify the alternative hypothesis in each example here. So generally accepted among educators that the average student studies no more than 15 hours per week. A national student organization claimed that its members study more than the national average. So more than, that's a hint right there. Okay, so the null hypothesis here, okay, the null hypothesis is that the average or mean amount of study is not more than, that would be at most 15 hours per week. The alternative then would be that the mean is greater than 15 or more than 15 hours per week. So that's how we set up the hypotheses there. A leading news authority claims that the president's approval rating, let me change my ink color here. President's approval rating has dropped over the past 3 months. Previous polls put the president's approval rating at a minimum rate of 56%. Minimum rating of 56%. The president's chief of staff wishes to test the claim since an election is approaching. Okay, so what would the null hypothesis be in this case? So we've got percentages here, yes? So percentage is population proportion. Well, the chief of staff is claiming that the proportion is probably more than 56%, I would imagine. So it says that the leading news authority claims that the president's approval rating has dropped over the past 3 months. All right, so dropped would mean less than, which means that the null hypothesis is that it's been at least 56%. So this is the claim. This is the claim from the news authority, not from the chief of staff. The chief of staff would like to find out, is it in fact dropping? And if it is, then we can maybe they put out some more advertisements, or have the president do some things to improve his or her rating. Excuse me. Leading authorities have stated that approximately 1% of dogs attack people, even if the dogs are unprovoked. An animal rights organization believes the 1% is not accurate. So the null hypothesis here is that the percentage of dogs is 1%. The alternative here is that it's not. P is not 1%. So here's the analogy I referred to earlier regarding the criminal justice system. And if you're not familiar with court trials, we have a defendant, we have a plaintiff. Now this is true whether it's a criminal or whether it's a civil trial. Now in a criminal trial you have a prosecutor instead of a plaintiff. The prosecutor is the district attorney, or the chief prosecutor here, who is trying the patient, trying to prove that not the patient, but trying the defendant, trying that prove that the defendant is guilty beyond a reasonable doubt. Okay. So when we do these hypothesis tests, we're using this idea of a criminal trial here. All right. The defendant is the one under attack being prosecuted, and the plaintiff or the prosecutor is presenting the case against the defendant. The defendant is assumed innocent until proven guilty, and the plaintiff needs to prove guilt beyond a reasonable doubt. So here what we have is that the status quo is the null hypothesis, and the alternative hypothesis is challenging this. In other words, the prosecutor is saying, "You're wrong." In other words, you're guilty, right? So if the prosecutor can prove that the defendant is guilty, then the defendant goes to jail. All right. However, the defendant is assumed innocent until proven guilty. So the burden of proof is on the plaintiff. The burden of proof is on checking the alternative hypothesis, which is what we do in the hypothesis test. The null is accepted status quo, and in order to be rejected, must be proved beyond a statistical doubt. Since the alternative will replace the null as status quo, it needs to prove its case significantly. So we'll talk about what that means and what enables us to do that. All right, so there's a couple ways to perform the test, one of which is called a test statistic. There's no jury, but the evidence depends on the idea that a random sample should produce values close to the population parameter, whether it's p or mu. So toss a coin 100 times. If only 20 heads come up, we might conclude that it's not a fair coin because it should be closer to 50. Not exactly 50 necessarily, but closer. How much evidence is necessary? Good question. We say that the evidence is overwhelming if it is statistically significant, meaning that it would be highly unlikely to occur if the null hypothesis were indeed true. We say that our results are statistically significant if they exceed our level of significance, which is called alpha. Now, alpha is determined by 1 minus the DOC. What's DOC, you say? That's the degree of confidence that we're after. So if we are after a 95% degree of confidence, that means that alpha is 1 minus 95%, or 0.05. So in general, if we're after a 95% degree of confidence, then this is the number that we're trying to get close to or be less than. So anyway. The level of significance is akin to the concept of reasonable doubt. The goal is to surpass the bar of reasonable doubt here. And it is related directly to the level of confidence, as I said. It's a measure of how confident we are that the population parameter lies within our confidence interval. We've talked about confidence intervals. C is a confidence level. Alpha is 1 minus C. So if we have a 95% degree of confidence here, then that means that 95% of all the values fall between the two values. So you may recall that when we're finding z-scores, there's either a table or you're using the inverse normal to determine the value of 1.96. If you have questions about that, where that 1.96 came from, let me know. Okay. All right. The level of significance is the total area of both tails. So that's this plus this. So if alpha is 0.05, that means that half of that is 2.5%, which means that 2.5% is going here, and 2.5% is going here as well. Okay. So after the evidence is weighed, a conclusion must be drawn. Oops. If the evidence is overwhelming, we reject the null hypothesis in favor of the alternative, which is, again, this is what we hope to have happened. And when I say we, I mean the students or the instructor or whoever it is performing this hypothesis test. So you're always testing the null hypothesis, but you're hoping to the alternative be true. Right? If the evidence is not shown to be significant, statistically, we fail to reject the null hypothesis. So the analogy here is that the defendant is found not guilty. Okay, the defendant is found not guilty does not necessarily mean that the defendant did not do the crime, right? It just means that there was not enough proof offered or evidence offered to prove beyond a reasonable doubt. So be aware that not guilty and innocent are not the same thing, right? Not guilty is not equal to the same as innocent. We aren't concluding that the null hypothesis is true. Instead, we conclude that the evidence against it is not compelling enough to reject it. So, when I think of status quo, i.e., the null hypothesis, I imagine the defendant is sitting at home, defendant is sitting at home watching TV, right? Resting, happy, and so on, right? But then the police knock on the door and say you're under arrest, and then the defendant is given a court trial, right? And then they have to prove, to keep the defendant in jail, they have to prove that he or she is guilty. If we fail to reject, we have not done that. We fail to reject, the defendant goes free, like I said, not guilty. However, if we do reject the null hypothesis, we have proven our case, and then we have a guilty verdict. I hope this helps. Okay, finding a defendant not guilty is not the same as finding him or her innocent. It is generally accepted among leading educators that the average student studies no more than 15 hours per week. In the spring newsletter, a national student organization claims that its members study more per week than the national average. Okay, so there's the claim. After performing a hypothesis test, the researcher's conclusion is to reject the null hypothesis. Do the researcher's findings support the organization's claim? So remember that the organization claims that the members study more than the national average. So let's see what the status quo is here, is that the mean study value is no more than 15 hours per week. Right? No more than 15 per week. So the alternative, would be the claim, which is that the average is more, at least for that organization, right? For that body of students. They claim that their average is more than 15. They do the hypothesis test, let's call it HT, right? They perform the hypothesis test, it's all finished, and the conclusion is that we failed to reject FTR. We failed to reject the null hypothesis. So remember what the example was here with the defendant. The defendant is not proven guilty, right? Which means that the claim is not supported. The claim is not supported since the opposite of the claim was not rejected. Okay. So the null would represent the idea that the organization's members are the same as the general population. Oh, sorry, I thought it said fail to reject the null hypothesis. Well, in the case that they failed to reject, of course, the answer is no. Of course, I misread that. So reject, of course, would be yes. So reject a null hypothesis means that they were proven guilty. Okay, so the answer is yes, since we rejected the null hypothesis. Anyway, sorry for the confusion there. But if it was a fail to reject, of course the answer would be no. Board of Education for one large school district uses at least 10%, which writes like this, as the percentage of high school sophomores considering dropping out of school. That would be your null hypothesis. A high school counselor in this district claims that this percentage is too high. This is the claim. The percentage is lower than 10%. That's the alternative. A hypothesis test is done with a significance level of 2%, which means what for the degree of confidence? That's right, 98%. Okay. On the counselor's claim. The result is to fail to reject. All right, so I'm reading this correctly this time. Fail to reject the null hypothesis. Do the findings support the counselor's claim? So once again, what is the counselor's claim? Let's read it again. A high school counselor in this district claims that the percentage is too high, i.e. less than 10%. So if we're testing that claim and we failed to reject the null hypothesis, in this case, do the findings support the counselor's claim, yes or no? There's the null and the alternative. And here we say that there's not enough evidence to reject the Board of Education's claims. In other words, not enough evidence to reject. So failing to reject is sort of a, it doesn't, once again, the defendant is set free, but it doesn't mean that they're innocent, right? So the answer to the question is the counselor's claim is not supported. Doesn't mean he's wrong. It's just there's not enough evidence at this point to, not enough to support the idea that the population proportion is less than 10%. Now, you could redo the study, right? You could redo the study. You could change the significance level. You could change certain things, but ultimately it's not supported. So the three different tests that you're going to look at, and this is going to correspond to your calculator as well, are if there's a less than in the alternative hypothesis, then we call that a left-tailed test. So areas to the left. So left-tailed, less than, left. And on the picture, when you're using a test statistic, the area is to the left. Let's say if it's a Z, for example, right? That's a left-tailed. LTT, left-tailed test. If on the alternative hypothesis, we have a greater than value, so for example, mu is greater than 25 or something like that, then we have a right-tailed test. So a right-tailed test would be, here's a test statistic T, that's a right-tailed test. Finally, when there's a not equal to value in the alternative hypothesis, so if said mu is not equal to 17, then we would use a two-tailed test where alpha is spread between two values to the right and to the left of the T or Z test statistic. So once again, the main thing to remember is that when there's a less than in the it's left-tailed. When there's a greater than, it's right-tailed, and when there's a not equal to, it's two-tailed. Conclusion rule for rejection regions. Reject the null hypothesis if the test statistic falls within the rejection region. We're not going to use this for every time, but it is nice to see the definition, because when we look at the test statistic, it's helpful to visualize that. So if the rejection region consists of this space and this space, and if the test statistic, let's say T, right there, falls outside of that space, would we reject or fail to reject? The answer is that we would fail to reject the null hypothesis. However, if the test statistic, let's say that this is the rejection region, and then we have the same test statistic as before. Notice now that the test statistic does fall within the region, so we would reject the null hypothesis. So that's the visualization there, is that when the test statistic falls outside of that region, you might be wondering, well, where does this value and where does this value come from? That's a good question. That value comes from the inverse t when you don't know sigma, or it comes from the inverse normal when you know the sigma value. It is also called the z-score or t-score. So for a left-tailed test, here we have negative z alpha, critical value. And we reject the null hypothesis if the test statistic falls in that region. So once again, if z sub t, the test statistic, falls in that area, then we reject. However, if it falls to the right of that for a left-tailed test, we fail to reject. Once again, we're not going to be using this necessarily as our criteria, but it's nice to visualize. Okay. Furthermore, the p-value is defined as the area to the left of the test statistic in a left-tailed test. This is called the p-value. So you'll note that the p-value has a smaller area than the total area here. So if I was to change the color here, if I was to include this red region here as well as the black, is it pretty clear that the black region is smaller than that? And so that's what we're doing when we're using the p-value method for testing the hypothesis. Let's keep going. All right. For a right-tailed test, it looks like this. Reject if it's to the right, fail to reject if it's to the left. For a two-tailed test, remember that it's alpha over 2 over here and alpha over 2 over here. So that changes the values a little bit, but it doesn't change the rule. So if the test statistic falls here or here, we reject the null hypothesis. However, if the test statistic falls here or here, anywhere in there, we fail to reject. All right, so here's the calculation for the test statistic for population mean and proportion. So for the mean, we use the sample statistics here. So sample mean, population mean that we're comparison, so you can call that the comparison mean. In other words, if the alternative hypothesis says that mu is greater than 85.8, then that value is the 85.8. If the x bar is 88, and if the s is 4.5, and the n is 100, then the test statistic, and you can call this z sub t if you want to remind yourself that it's a test statistic, is calculated by taking x bar minus the mu over s over the square root of n, like that. So in my calculator, I could do 88, actually let me do parentheses, 88 minus 85.8 divided by standard deviation over square root of 100. Close that paren, then close that paren. So 4.89 approximately. So the test statistic here would be 4.89, which is a z-score, right? This is a z-score. So if I was to draw the normal distribution, you know that the z-scores center at 0. 4.89 is way up here, right? 4.89. So if this is in the rejection region, then we're set. And you may recall that for a 95% degree of confidence, the rejection region includes that value because the z star, which is the value that separates the rejection region, is 1.96. So there's 1.96 over here. So is it pretty clear then that the test statistic falls within the rejection region? So in that case, we would reject the null hypothesis. Okay, so that sort of goes through an example there, using the test statistic for the comparison mean. Again, we utilize the z-value to identify the rejection region and determine whether reject or fail to reject Ho. For a proportion, we have a couple of conditions that need to be met. We need the sample size multiplied by the probability, or the population parameter, I should say, population proportion. We need the product of those two numbers to be at least as big as 5, and the product of those two numbers to be at least as big as 5 as well. So this one is sort of cut off, but n times 1 minus p, which is n times q, needs to be at least as big as 5. So for example, if we had a sample size of 100, like we did in the last example, and let's say that the null hypothesis claims that the proportion of something is 52%, and the alternative says not 52%, then the p-value is the 52%. The n value is 100. So 100 times 0.52 is what? That's 52. And is 52 larger than 5? Yes, it is. And then if I was to take 100 times 100 minus 100% minus p, that would still be large enough. That's still bigger than 5. So that's the thing that you would want to check there. And then assuming that those work, we can say that the sampling distribution for the sample proportion is normal or close to normal, and we can use the z-score. So notice that this is a p-hat, that's the sample proportion. This is the population or compared proportion, which is the number we looked at right there, right? And as is that, the 0.52, as is that, the 0.52, right? So if the p-hat value was, let's say, 54%, then we'd be testing the claim that the population of whatever it is 52%. Okay? The claim here actually is that it's not equal to 52%. So if we got an average of 50, or I should say a percentage of 54% with a sample size of 100, we could test that claim. So for now, at least for the test statistic formula, we could say, oops, did I lose it? Looks like I lost it. Oh well. See if I can remember the values. So, see, I think it was, let's say 54% minus 52%. Divided by the square root 52 times 48% divided by n is 100. Close. Okay, so there's your test statistic there is 0.4 basically. 0.400. So then once again, here's 0, here's 0.4. So depending on your degree of confidence, if it was 95%, that falls outside the rejection region, even though there's a negative 1.96 here as well. So because it falls outside the rejection region for a two-tailed or a right-tailed or a left-tailed test, we would say that we would fail to reject the null hypothesis here. In other words, we cannot support the claim that the average or that the population proportion is 54%. So again, that's sort of that's the test statistic method. We're also going to use what's called a p-value method here. In a sample of 88 adults selected randomly from one town, it is found that 4 of them have been exposed to a particular strain of the flu. At the 0.01 significance level, test the claim that the proportion of all adults in the town that have been exposed differs from the nationwide percentage of 8%. So let's identify the null hypothesis. It says differs from the nationwide percentage of 8%. So proportion is 8%. Claim the proportion is not 8%. Might be more, it might be less. The number of successes here is 4. The number of in the sample is 88. P hat is defined as x divided by n. P hat is defined as the number of quote-unquote successes. Now I realize that someone having the flu is not normally considered a success or a good thing, but that is how we define x. So 4 divided by 88 gives us about 45.5%. And it says at the 0.01 significance level. So that means that alpha is 0.01, which means that the degree of confidence is 99%. So in this case, we are looking at a two-tailed test. So we're going to establish the hypotheses here. And then we're going to determine the critical values for the confidence and significance level given. All right, so for a 99% degree of confidence for a two-tailed test, we have plus or minus 2.576. So that's 2.5 standard deviations above the mean and 2.5 standard deviations below the mean. Once we determine our test statistic, we just check to see whether it falls in or out of the rejection region here. So the test statistic calculation, as before, p hat minus p over all of that, end up with a negative 1.195. So can you think about where this goes in relation to these numbers? That's right, negative 1.195 goes about here. That's the z sub t that we just found. Therefore, falls in the non-rejection region. Therefore, we failed to reject the null hypothesis. And when we fail to reject, we set the defendant free. He's not innocent necessarily, but we set him free. Not enough evidence to convict. Therefore, not enough evidence to support the claim that the adults of that particular town have a percentage of flu sufferers that differs from the nationwide percentage of 8%. So it's a mouthful, to be sure. Failed to reject the null hypothesis. There is insufficient evidence to conclude that the proportion of adults exposed to the flu differs from the nationwide average. Now, there is a shortcut method for doing this, and some calculators differ from others, okay? So if I were to go stat over to tests, and then if we were to use a proportion test here, prop z test, then what we do is we fill out the appropriate information as given. So the proportion that is being compared to is the 8%. The number of successes here was that were 4, right? 4 people had the flu out of 88 people. Also, it was a not equal to P not, as opposed to a less than, which is a left-tailed, or a right greater than, which is a two-tailed. Then we go to calculate, and there's the negative 1.195, which was the test statistic. You'll also note that the p-value here is given as 23 or 0.2322. The other way of determining whether we reject or fail to reject is we compare the 0.2322 or 0.232, let's say. We compare the 0.232 with the alpha value, which was 1%. If the p-value is greater than alpha, we fail to reject, which is exactly what we did here, right? If the p-value is less than or equal to alpha, we reject the null hypothesis. So this is consistent with that. So the alternate method here is using the p-value here. So the calculator is not giving you the conclusion to the hypothesis test. It's just giving you enough information to be able to tell. And then remember, you may recall or may not, that the other thing you can do with the prop z test is instead of calculating the values, you can actually draw the picture. It will draw the picture for you. So when you draw the picture, you see that the z value is given there, and that the p-value is given, right? So this is the test statistic. The rejection region's way out here. So this is way outside of the rejection region here. So as I mentioned, the p-value, the definition of the p-value really is the probability of obtaining a sample more extreme than the one observed in your data. So calculating the p-value is essentially, once you determine your test statistic, say z sub t, once you determine the test statistic, let's say it's a left-tailed test, for example, that is the p-value. That is the p-value right there, is that area. So the p-value is the area to the left or to the right of the test statistic, given depending on whether it's a left or a right-tailed test. If it's a two-tailed test, then we're saying that the area to the right or the left of the test statistic, depending on the position of 0, and then we double that value. So if this was, 3%, then the p-value would be double that, which is 6%. And we'd have to compare that with alpha. Is it greater than alpha? Is it less than or equal to alpha? For the left-tailed test, we calculate the p-value for a hypothesis test with the following hypotheses. Assume the data has been collected and the test statistic is negative 1.27. So as I mentioned, it's a left-tailed test. There's your negative 1.27. We really just need to determine the area to the left. Come back later, I'm busy. Sorry about that. Anyway, so we use the normal CDF. That was the janitor, by the way, trying to do his job. Anyway, so we would go to the second distribution menu, normal CDF. As you can see from the picture, that we would use a small value of, say, negative 10,000 or 1,000, negative 1.27, 0 and 1. It's 0 and 1 because we have a standard normal distribution here, right? So there's the p-value, 0.1020. So there is the mean, okay? So once again, determining the null and null and alternative hypotheses here. There's the picture I drew earlier. There's the p-value. So if let's say that we now have a degree of confidence of 95%, which means that alpha is 5%, which means that the p-value, which is 10, that's 10% basically, that's greater, the p-value is greater than alpha. P-value is greater than alpha. Therefore, we would fail to reject the null hypothesis in that case. Now, if the degree of confidence was different, then that might change the result. Okay. All right. So the right-tailed test would look like this. So if we have a test statistic that's 2.21, and then the alternative says less than or equal to 1.8, and the null says less than or equal to, the alternative says mu is greater than 1.8, we have what would be a right-tailed test here in this case. So here's the picture. We're finding the area to the right of 2.21. So take a minute to think about or to calculate the area to the right of that value. Remember, it's a normal distribution. So it would be the normal CDF once again, where the small value is 2.21, the large value is infinity, 0 and 1. So 0.0136 approximately. There it is. So there's a 1.36 probability that value more extreme, would be selected if the null hypothesis is indeed true. Try not to go down too far down that rabbit hole, but that is what we're looking at when we say the p-value. So for a two-tailed test, here's another example here. Test statistic negative 1.99 here. We need to find the area to the left of that. But since it's a two-tailed test, we'd need to multiply it. So this is p over 2. This is half the p-value. So if the area to the left is 2.3% here, we'd need to double that, right? So if p over 2 is 2.33%, that would say that p is 0.0466 or 4.66%, which is illustrated down there. All right. So in the case of they're just giving you the test statistic, then using the prop z-test or the z-test or the t-test doesn't make a whole lot of sense because you're not typing in all the information here. But all you'd need to do, and we talked, some of us talked about this earlier this week, is that you would just draw the picture, find the 2.12, find the area to the right of this, because this is a right-tailed test, because greater than points to the right, yeah? So that would simply be, once again, normal CDF. Minimum value is 2.12. Maximum value is 10,000 or so. 0 and 1. So 0.017. Okay. So the p-value is approximately 0.017. So if the alpha was 0.05, then that would be less than alpha. So here's another example here. So go ahead and try this in your calculator. See if you can find the p-value. First, ask yourself what type of a test this is. And this is a hint right here. Would this be a left-tailed, right-tailed, or two-tailed test? So it's a two-tailed test. And if you checked it in your calculator, you should get 0.1188. Finally, would this be a left, right, or a two-tailed test? It is a right-tailed test. There's your test statistic, so find the p-value now and hit pause. And hopefully your p-value came out to be that. Now, sometimes the p-value comes out really small, so if your calculator says, 5.26 da 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 e negative 5, for example, this is scientific notation. So 1, 2, 3, 4, 5 spaces to the left means approximately 0.000526. So if you're rounding this to the fourth decimal place, that would come out to 0.0001 or 1/10,000th. Okay, so be aware that the scientific notation that the calculator gives will need to be rounded if you're calculating numbers in WAMAP. Now that we know how to find the p-value, how is it used to draw conclusions in a hypothesis test? That's the last piece of the puzzle. So we compare it to the chosen significance level alpha, and if p is less than or equal to alpha, we reject the null hypothesis, which means that we accept the proposed conclusion of the alternative hypothesis. If we have a p-value that's greater than the significance level, then we fail to reject the null hypothesis, which means that we would not accept the alternative hypothesis given. This is an A, sorry. Okay, so we have a p-value here for a given hypothesis test. If the stated significance level is alpha equals 0.05, what is the conclusion? Based on what I've talked about earlier, this should not be difficult. The question is this less than, equal to, or greater than 0.05? It is less than, because this is 123 10,000ths, and this is 500ths, which is much larger. So, since this is less than, we would reject the null hypothesis, which means that we would accept the conclusion of the, oops, I totally misspelled that. We would accept the alternative hypothesis that was given. If the level of confidence is 99%, what is the conclusion to the hypothesis test? So you would calculate alpha here to be 1%, which was 1 minus the 0.99, and then reestablish the order of these numbers. Is this greater than, less than, or equal to this number? This time it's greater than. If you want to put zeros here, that helps. This is 123 10,000ths, and this is 100 10,000ths. So this is a greater than sign. Therefore, we would fail to reject the null hypothesis. Therefore, we cannot accept the alternative hypothesis. There's not enough evidence to support the claim. So the p-value approach is what we've been working on here. First, we state the null and the alternative hypotheses, which are abbreviated HO and HA. We set up the hypothesis test by choosing and stating the level of significance. Alpha is 1 minus the degree of confidence. Gather data and calculate the test statistic. Find the p-value of the test statistic and compare it to the significance level. draw a conclusion based on the above comparison. Okay, so those are the steps that we follow in order to determine, and then don't forget to give your conclusion as a sentence or paragraph. We don't want to just say, fail to reject Ho, and then move on with our day. We actually want to put that back into context with units. So if the units were, rubber duckies, and the claim was that the mean number of rubber duckies produced per day was greater than 10,000, and then the claim was let's say that we rejected the null hypothesis, which means that we accept the alternative hypothesis that the mean number of rubber duckies was greater than 10,000 per day. So then we would say that in a sentence, the claim that the average number of rubber duckies was larger, sorry, I'm using abbreviations here, larger than 10,000 is supported by the sample data. Something like that. Okay. So try this problem. Hit pause and try the problem, and then come back for the solution. All right, so here's the null and alternative. Here's the picture supporting it. We do want to double check that the product of the sample size and the p is large enough, which it is. Same thing there. We are all right to proceed. So there's our p hat. Test statistic value. P-value 5% plus a little bit extra. Just a little tiny bit greater than, so we just missed it. So you might wonder, well, how could we make that number small enough to actually support the claim? Well, maybe make the sample size larger. So if the sample size had been 500, maybe we would have succeeded here. So something to think about. So when we're redoing the experiment, make the sample size bigger. Okay. Dawn believes that less than 1/3 of the students on campus hold a part-time job while in school. To test this claim, he randomly selects 116 students for whom he collects the following information. 32 for yes. In other words, yes, they hold a part-time job, and 84, those should add up to 116. So what is our successes? That's right, it's 32. What is the number of people polled? 116. So what is the null hypothesis here? Well, the alternative hypothesis is certainly that the proportion is less than 1/3, which is 33.3%, right? 3 bar percent, and this is greater than or equal to 33.3 bar percent. Or we just say 0.333. Do the evidence support the claim at the 0.05 significance level? So here we can use the prop z test, stat, prop z test. The p naught is the 0.333. The x is 32. The n is 116. And since we are going with less than, that's going to be a left-tailed test. P-value is 0.0958. P-value is 0.0958, I believe. So the p-value is greater, 0.09, excuse me, is still greater than 5%. So no, fail to reject. A hospital that welcomes poor and homeless patients believes that the percentage of non-paying patients is no longer 35%. No longer equal to would be not equal to. That's a proportion, 35%. That's the alternative. So the null hypothesis would be equal to 35%. From a random sample, 97 of them are unable to pay, for a total of 250 on the sample size. Does the evidence support the organization's claim that the percentage of non-paying patients is not 35%? Sorry for the double negative there. If this helps, just say poor. Poor patients isn't 35%, which is this claim here, at the 0.01%, 0.01 level of significance. So same idea with the calculator here. Prop Z test is same deal. Here we do the prop Z test with the compared proportion, which is 35%, where X is 97, N is 250. This is a not equal to, so this would be a two-tailed, and we have a calculate. So 0.2078. So we fail to reject. P is much greater than alpha, so fail to reject. Therefore, no, not sufficient evidence. To support the claim. And that concludes this video. I hope that you learned at least something here, and I enjoyed teaching you. Thank you.